So at the moment, we've got the topology file that contains all of the information about the bonds and all of the interactions that we're using for this run. We have our conf.out.grow, so the final frame of the last simulation, the energy minimization simulation we've run. We've copied that across. We've got our npt.mdp file, which will define all of the molecular dynamics parameters we want to use for this simulation. And we've got another Slurm submission script. So let's have a quick look at our npt file. And you'll notice that there are certain things that are quite different. The first one is our integrator, rather than being steep, is now MD, and that's because we want to use the leapfrog molecular dynamics algorithm. So now we'll actually be running proper molecular dynamics rather than just equilibrating our system. Our time step also has increased. We want to run with a time step of, that is definitely not 2 femtoseconds, rather than nanoseconds. We want to run with a time step of 2 femtoseconds. And we want to run our simulation for 500,000 time steps. The log outputs are exactly the same as they were before. Here we add some constraints, and the constraint H bond just says that for your the protein, all of the hydrogen bonds in that protein, we will simulate as if they are rigid. And the method that we'll use to simulate this is an algorithm called links. And that's just to ensure that when your particles move, because of course your particle will be moving, you don't want your hydrogen to just stay in place fixed in your simulation box. You want it to move sensibly along with the atom. So that algorithm will do that for you. You can find out more about this by looking in the Gromacs page. Here we define our van der Waals interactions. So we want a cutoff at 1 nanometer. We're using the Verlet cutoffs. Cutoff method, just like we did last time. And here the DISP core, which I think is dispersion correction is what it stands for. We're saying that we want both the energy and the pressure to be corrected because at that cutoff, there's of course going to be a jump in your energy, a tiny jump, but jump in energy from whatever the energy actually is to 0 as you reset everything towards 0. And what we're saying here is we're saying we'd like Gromacs to do a correction so that smooths it out a bit and is a bit more physical. And then finally, we've defined our periodic boundary conditions as being, our system as being periodic in all 3 dimensions. Coulombic interactions, we've got exactly the same things as before. And now the last 2 things we have are new. We've set up a thermostat that uses velocity rescaling to ensure that our system has a constant or near constant temperature throughout the simulation. And we've set up a barostat, in this case, we're using the Paranello-Raman barostat to ensure that our simulation has a constant pressure throughout the simulation run. So for the thermostat, you need to define for every single part of your system what temperature you want them to be fixed at. And so I've set everything to be at 300. And then you want to define as well a tau t, and that just defines how much fluctuation you're going to allow on the temperature. Because of course, in a physical system, the temperature of every particle is going to vary a bit. But if you fix the temperature exactly, you're not going to give very much, you're going to end up with very, very weird simulation results. And likewise for the barostat, you set the pressure in bars rather than atmospheres. And the tau pressure is also very similar. It's the coupling time. It's sort of how long you can think of tau t and tau p almost as defining over what sort of time scale am I okay for this to average the temperature or the pressure that I'm aiming for. And finally, you've got the compressibility of your system, which should be this if you're running anything that's water or has water in a lot of water in it. Great. So at this point, we will use exactly like before the Gromacs pre-processing tool. And this time you'll notice that it did not complain about labor lists. And we'll get to why in a sec, actually, because perhaps it should have. And then we shall run our simulation. And as you can see, it's running. It's running, and it's going to take about 7 minutes to run. So before it finishes, I wanted to talk about a couple of things that we've not really discussed, but that I'd like to really quickly glance on. The first one is you may have noticed that here I had to define the neighbor list, how often the neighbor list is updated and things like that. So one of the questions is links similar to shake in lamps? Yes, links is just it's another parameter. If I go on the, there it is. If I go on the Gromacs page for molecular dynamics files, and if I go links, you'll notice the constraint algorithm, the one that it has afterwards is shake. It's just got links and shake. So it's exactly the same idea, just does it in a slightly different way. Cool. And that's actually, that's really useful, by the way. You can find all of the parameters you can use, and there's a ton of them. You can find them all in the Gromacs manual. Including all of the integrators you can use and everything, things like that. Now, one of the things I wanted to draw your attention to is that when we did the minimization, we set a neighbor list frequency, but we did not set a neighbor list frequency or update frequency when running our final NPT run. And why is that? Well, part of the reason why that is because for some of these parameters, they have a default value. So for instance, NST list is by default set as 10. So if you don't put anything, Gromacs will always say, oh, that's 10. And then you can define it to something else if you want. But for a lot of these, they have default values. So for instance, the default value for NST log is 1000, which means that Gromacs will by default output to the log file every 1000 time steps, that sort of thing. So that can be useful, because it means you don't need to define everything, but it also means you should really be careful sometimes if you're running something that Gromacs doesn't expect you to run. And frankly, Gromacs mainly expects you to run biochemical systems. If you're doing something a bit weirder than that, then you should really check that you don't have any unexpected parameters that are set at values that you don't want them to be set at. And now the final quick thing I wanted to talk about is periodic boundary conditions. And boundary conditions, so it's always a question with your simulations, what you do at the boundaries of your simulation box. And that can be a really big problem, because if you're just simulating your simulation box, the simulation box that you've built without considering anything that happens there, you're either going to end up running a simulation where there's a vacuum outside of all your boxes, which means that all of your edge atoms, edge particles, are going to be interacting with a vacuum on one side and then your simulation on the other, which is going to lead to some weird results. Or you might, or you're simulating essentially a surface at the edge of every box, and then you've got an interaction with a very weird, very hyper smooth surface, which is also not realistic. So one of the ways that people have found to get around this is to apply periodic boundary conditions, or PBCs. And these are just a method of simulating your system as if it's in bulk. And the way it works is that you sort of consider your system, your simulation box, to be a box at the center of a crystal of replica of your box. So you've got your box here, and then you've got like a replica of it to the left, to the right, to the top, to the bottom, to the front, to the back, all of that. And what that means is when an atom sort of leaves your simulation box from the left-hand side, you'll have another one coming in from through the right-hand side, or as it is in this picture, if it leaves through the right-hand side, you've got a replica of it entering through the left-hand side. This is excellent for a number of things. For one, you don't have to worry too much about your boundary effects, but then also for things like your long-ranged interactions, Well, all of a sudden, instead of simulating just your box, you're effectively simulating a massive crystal of which your simulation box is the unit cell. And that means that you're able to consider long-range electrostatic-like interactions. You can solve this to a really high degree of accuracy by using things like Fourier transforms. So it's one of those things of not only does it make your system more realistic, but it makes certain things easier to calculate, which is great. Now, one of the things that you need to be really careful with when using periodic boundary conditions is there's loads of ways that they can go wrong. So you need to be careful about what you're doing. For instance, if your system is too small, you might end up with in the situation where one of your particles is within cutoff distance of its periodic image, which means that you end up with a situation where your particle is acting on itself and thereby affecting its position. And that's really not physical. Cool. So with that, I will very briefly, actually I can just show you these results even though it's still running, and then pass on to Holly. There we go. So you can see my simulation is still running. But if I run ls-lrt, so you'll notice that I'm getting very much the same styles of outputs as I was before. So I've got my trajectory file, I've got my slurm file, I've got my MD file, my energy file, things like that. So all of the same types of files are being produced. And when my simulation runs, when my simulation completes, I'll get two other files produced. Actually, it's very close to completion at this point, I suspect. But I'll get two extra files produced. The first one is going to be the confout.grow file, which is, actually what it's going to do is it's going to back up the one I copied and create a new one. Ah, perfect, it's finished. So it's created a new confout.grow file after copying the first one I'd run. And then the other thing it's added that wasn't there before during our energy minimization is a state.cpt file. And what that does is it contains all of the information from our thermostat and barostat, so that if I wanted to rerun the simulation, it could read in the final point of those to get an idea of where they were in their curves and make sure that there's no discrepancy in the energy and the pressure and temperature of the system. Cool. So that was a quick bullet tour of bullet train tour of how to run simulations in molecular dynamics using Gromacs. How to run molecular dynamic simulations using Gromacs. And now I think that Holly will, well, before Holly takes over, I want to check. Please do let me know whether you have any questions. I'll be happy to answer them. And if not, I guess I will let Holly talk about visualizing and extracting data from these.
Thank you. So yes, as mentioned, I will be talking about visualization of your system and extracting data from your system. So let me just share this tab. So as previously mentioned, Gromacs comes with a load of post-processing tools. This section will comment on a few of those and also have a look at visualizing your system with VMD and plotting output from Gromacs. So yeah, the first thing we're going to do is look at some of the thermodynamic properties of the system that we just ran. So I will now share my terminal screen. Okay, great. So I've just run the simulation that we did in the last exercise. You can see I've got a number of outputs from this simulation. So I'll go through some of these. you can see, you've got the conf out, so this is your coordinates from your output, which was run. This enr.edr file, which contains energy information, which Julian mentioned in the last lesson, and we also have this trash file. It contains information about the trajectory, and state.cpt file. So this is a checkpoint file, which takes a snapshot of the final state of your system, and then this can be used in restarting your simulation or continuing it. So if your simulation hasn't run to completion, you might not see some of these in your directory. In that case, you'll have to wait a bit longer for it to complete. So what I've actually done is copied these into some of these into a different directory. So these are the files that we're going to be looking at during this session. Has anyone not had their simulation finish before I go on from the last part? So it should take about 7.5 minutes, I think, was what I saw. Yeah, just because you'll need some of these files. But I think we can probably move on and look at the enr.edr file. So we saw a bit in the last session. You can use this Gromacs energy tool for extracting information about your simulation from this .edr file that you generate. So I think this is just, yeah, it's a big binary file, some information in it. So with your Gromacs energy tool, you can basically take this, read in this file, and then create an output file of something you might be interested in. For example, if I want to monitor the temperature throughout my simulation, and this has the default format of .xvg, which is a format which is usually read in by xmgrace, which is a plotting tool. Now, if you run this command, you'll see that you have a lot of options for different things to select, bonds, angles. Probably some of the most interesting ones are your potential energy, kinetic energy, your total energy, conserved quantity, and temperature. So if you select a number here, that will be what's plotted. So in this case, if we want to look at the temperature, okay, thanks, Julian. That'll be helpful. If anyone hasn't managed to get their simulation to finish, you can find the results generated in that shared directory. Okay, so yeah, basically you choose what you want to plot here. You can choose more than one thing, which is quite helpful. So if I wanted to choose temperature, and then I'm free to enter another number and keep pressing enter, and it will plot multiple things in the same file. But for now, I'm just going to plot the temperature in this file. And then it prints some information about the drift and the average temperature and the root mean squared. And then we should have this file, our temp, xvg. The split at the top is all the xvg format, so this all tells you it's created by Gromacs Energy. And then it contains some formatted information which will be helpful if you're plotting it with xmgrace. And then the data itself, so this is time step, or yeah, time in picoseconds, and the temperature. So fortunately on Arch 2 we don't have xmgrace, so you can't plot this as it is. However, we do have GNU plot, which you can access with module load GNU plot. However, that file we just looked at is not quite in the right format for GNU plot. What you can actually do instead is tell Gromacs to not do any of the XM Grace formatting. So you can have XVG none on the end. If you generate this again, you will see that it's cut out all this top bit. So this is quite helpful. Yeah, if you want to plot this with something that doesn't understand all that formatting, you can then plot this with GNU plot or similar, and say plot temp lines. Okay, and my X11 isn't working, so it's not showing me the plot itself, which is annoying, but usually a window would come up. I can probably fix that by logging in and logging back out again, but I might do that and might not have time to do that. But anyway, that should usually work. It's just that my viewer is not working. Yeah, okay. So I will actually just log in and log back in again, log out and log that in, log out and log back in again to fix the X11 connection. For some reason that's not working. But if I log back in, should be fine. So, work directory. See again. This has been very slow. Okay. Okay, so that has created a plot now. I just need to share a different screen in order for you to see it. And you can see you've got a plot of the temperature. So it starts off low, and as we heat the system up to 300 degrees Kelvin, and then it oscillates around 300. So that's doing exactly what you'd expect. Okay. So yeah, that's basically what the GMX energy tool does. It's really helpful for extracting data from your run. So what about visualizing your system? Well, on Arch 2 we have VMD, which stands for Visual Molecular Dynamics. You can use this with module load VMD. And that will load the VMD module. It's been very slow. Okay, great. You can now use it with the VMD command, and this will open VMD in a separate X11 window. I'm wondering if I can just share the screen. Okay, cool. I will share my entire screen on this side. Okay, so this will load the VMD window, and then it should also load some other bits that can be a little bit slow. Okay, great. So yes, this is the main VMD window, and then this will be where you'll actually visualize your atoms or protein. Across here, you can load a new file, so we want to load a new molecule. And the way you do this in Gromacs is you first have to load your .gro file, so your configuration file. So this one here, with all your coordinates in. So you can load that first. And you can see it's been loaded. And then as a next step, you can load files for this file, and then if you load in your trajectory file afterwards, it will load in the simulation. So visualize the movement of your atoms during the molecular dynamics simulation. So VMD has a load of different options. Won't go into them all, especially as it's being quite slow. Yeah, there's a lot of different extensions for doing analysis and looking at your data. It's a lot of different functions. But yeah, it's a handy way to visualize your system on Archer 2. Can be a little bit slow, especially with larger systems. Okay, I'm going to quit VMD. Okay, great. You can also do that as a shorthand way. You can do VMD and then your file, your .gro file, followed by your trav file, and then that should do exactly the same thing. I'm not going to do that now because I've already looked at it. Okay, the next thing I'd like to talk about is generating an index file. So I'm going to go back to just sharing the terminal screen because I think it's easier to read that way. Okay, cool. So we've got all these files. After you generated them, maybe you want to look at some properties of some specific group of atoms or range of atoms within your simulation. One way of doing this is creating an index file. So this stores basically just different groups of atoms. We can have a look at the format in a second, but to do this you use the Gromacs make index file, which is the shorthand NDX is the file name. Yeah, so Julian suggests you might want to do this on a local system rather than an HPC system. So it's quite slow when you're trying to do this over the internet, over the connection. But if you've got something very large that you want to analyze, it's usually better to move it off Archer 2, copy it off, and then do this locally with a lot less lag. But if you want to have a quick look at something on the fly, it's fine to use on Archer 2. So yes, to make index file, use make indx command. You need to supply a .gro file for this, so a coordinate file, and then you want to just give an output, so go back to 5pep. And then the extension is NDX for these index files. Oh, I have not loaded Gromacs. Do my module load has been so slow? Okay, there we go. Okay, so this is reading your grow file, saying there's no index files, that is true. And it's analysed. We've got this many protein residues, this many water residues, and 38 iron residues, which we know because we constructed it earlier. And then it's managed to split it into groups, which is really nice. So it's your protein atoms, protein hydrogens. It's found a group of C alpha atoms. It's done found the group of atoms making up the backbone of the protein chain. It's got a group of atoms in the main chain and lots of different things. So main chain plus hydrogens, side chain, protein masses, non-protein, your water atoms, number of sol atoms, which are the same because in our case we have water solution, non-water atoms. It's found your ions, your sodium atoms, and the waters and ions. So these are the default groups that it's managed to find. However, you might want to create a different group, and it's given you a load of different commands here that you can use to create new groups. So you can group by atoms or atom types, residue name, and then you have the options of naming the groups. There's different ways of grouping them, so you can do two commands and link them with a not option or an and option or an or option. So for example, if I wanted all atoms in the water, all oxygen atoms in the waters, you can do atom OW, because this is how they are named in the file. And it'll say, I found this many atoms with name OW. And yeah, this makes sense because we've got this many water atoms, so it's a third of this number. So it's found all the oxygens in the water molecules. If you now press enter again, you'll see it's added a new group, group number 18, and this contains all these atoms. Option, and if you type Q, this allows you to save and quit. And then if you then read your new index file, you can see how it's formatted. So basically, each of these directives gives the group name, and then it lists every single atom within that group. So your system is going to list everything. You can carry on through this. You have the protein here, all these different groups that we saw with the atoms, and then water. And at the very bottom, we should have our OWs that we just created. You can also give this a sensible name as well within while you're making the index file. Okay, so there's a short exercise now. I'd like you to try and use make NDX to create a group containing just the hydrogen atoms in the water molecules. So far I did it with OW, so all the oxygen molecules, but create a group with the hydrogen atoms in the water molecules. So this is slightly trickier because if you look at these OW, the oxygens and the waters are named just with OW, but the hydrogen ones have two separate names. So you're going to want to find the two different groups and then kind of group them together to form one group. So yeah, have a quick go at that and post anything in the chat. And also let me know if you have any questions as well. But we'll give, yeah, just a couple of minutes on that one. Sorry. So I tried plot. Oh, okay. So it should be with that should be with lines. So WL rather than W1. I'm not sure if that. I went a bit fast over that bit. I'll type it in the chat. Does that help? Okay, so does anyone have any ideas about? Okay, cannot find open files. No data in plot. Did that file get created? Did you run? Is it in your directory from when you ran GMX Energy? So it looks like it's not been either not found the file or something's gone wrong when making that file. I would double check that temp.xvg has the data you expect in it. Does anyone have any suggestions about the exercise for make NDX? If not, I will just go through it. Just keep the questions coming in if you're having issues with anything. Okay, so to do the exercise, we can do is run your make NDX command. Give this a new name. I think it matters. NDX. Right. So it's read all these groups again. So to get both the waters, these have the name of HW1 and HW2. So there's two different atom names for them. So what you can do is select, make sure you're getting the atoms HW1, and then use this OR command to use to group them both together. That seems a bit counterintuitive when you look at AND and OR, like maybe you'd think it would be you want this group and the next group, but it's kind of the logical operations here. So when you use AND, you're selecting an atom which is both in both groups. So if you tried to use HW1 and HW2, you'd get nothing because they're completely non-intersecting. So if you do this, it says it's found this many atoms with name HW1, this many atoms of HW2, they're the same. There's one hydrogen, two hydrogens in a moles molecule, and then it's created this new group, HW1, HW2, and then you can see that it's there. Okay, for the final bit, we'll look at doing a root mean squared deviation. This will be quite helpful when looking at analysis of atoms. In general, we're just going to look at this, but this is quite a similar format to how other analysis tools work within Gromacs. And you can see from the course notes, I've put a link to the list of different trajectory analyzing tools. But yeah, if you wanted to find the root mean squared deviation, Gromacs has a command for this. It's gmx RMS. And in this case, you want to take your TPR file and your trajectory file. And you can also supply an index file to this if you want to look at a particular group. And some kind of output file, and then you can set the timing as well, so it's in nanoseconds. And then in our example, you can select a group, and all these groups are listed from your index file. You can see here we have our extra group of oxygens in the water. But for this, we're going to select the protein backbone, so option 4, and then option 4 again for the RMSD. And then it reads your trajectory file, and then it will generate a file that you can then plot. In general, if you go to the Gromacs website, there's loads of different things for looking at different properties. Way too many for us to go into today, and probably not all of them relevant to our system. But that is the general format of how a lot of them work. Okay, final thing I'm going to look at is continuing your simulation. So this is really important if you run a simulation, or maybe it crashes midway through, or you run a simulation for so many steps, but then you find that you need to run it for a bit longer in order to see the properties that you want to see. So Gromacs makes these state checkpoint files as it's running, and usually it'll do a state.cpt, which we have here, and sometimes you get a state previous, which will be the last previous state. But this one here, it will be the state of the very end point of the simulation that we ran. So to restart a simulation, you can do this gmx md-run cpi state. In our case, though, our simulation actually finished, so it went to the end. We did all the MD steps that we wanted to do. So it didn't crash midway through, or it didn't run out of time in the job script. What you can actually do in this case, you can extend your simulation. So you can take your old TPR file and then create a new TPR file which has more MD steps in it, so which is set to do more MD steps. So this is done with the gmx convert TPR command, and then you supply this option with the extend. Let me share my screen. So yeah, this is how you can extend it. And then you can go ahead, and once you've got this new TPR file, you're able to then run it. And yeah, basically you just need to, this TPR file input, and then your state.cpt checkpoint file supplied in. So this would be the command that you would have in your job script. So a quick exercise you can maybe look at. So I'd like you to try and extend our simulation by 100 picoseconds and then submit the job. So if you need a job script, you can take the one we used before in the running exercise, running Gromacs exercise. Not Slim, what's it called? So, for example, what you'd need to do this is you need to run that convert TPR line on your original TPR file. So this was our MPT TPR, and then extend time to extend by, which is in picoseconds. So we can just add 100 here, and then -0 for our output file, and then we can have MPT new TPR. And then this gives you some information. So run start time. So this gives you the information about the old version, steps made during the run time for the run. So this did 1,000 picoseconds, and then we extend in the runtime by 100 picoseconds, and you can see here it's printed this information about how many steps it will do during the next simulation. And then if we want to then run this, we have GMX MD run. We want to take our new TPR, and then our state file, checkpoint file. And then if you submit this, this should do extension to the simulation. It's running now. A bit slow. Might complain that because I've moved it into a different directory, it might work. Okay, it didn't like that. So yeah, it wants the md.log from the other previous simulation. And okay, so it just wanted that file. And then that should run. Slow again. In the char file from the last time. I should get modified. Moved into a different directory, it's caused all kinds of problems. Okay. I should have just run this in the same directory. It's not being nice. Make it work this time. Okay, it looks like it's working this time. Yep. Why the output's so weird. Okay, so that's about all I want to cover today in the interest of time. Are there any questions on that part? Sorry, what do you mean about that question? We've just come to the end of the analysing and visualising section. So the very end part, continuing your simulation. The final exercise. Do you have any questions? If there aren't any questions, I think we're due a break. I'll just quickly check the...
Yeah. Shall we reconvene in 15 minutes? I think that the last session is quite flexible, so I feel it's more important to take a nice 15-minute break before coming back for the final session than it is to...
Yeah, that's fine.
So I guess with that, we'll meet back at 2:20, 2:40 even. See everyone then.
I think you mean 2:50, right?
Yes, that's how maths works. Yes. 2:50.
Okay. All right, brilliant. See you in a bit. If you have any questions as well, feel free to post them in the chat during the break.
Okay, I make it 10:02. Let me quickly share my screen. What do I want to show? Sorry, 1 second. It seems to be not letting me share my screen. Okay, give me a second. I'll just reload.
We saw it for a second. It came up.
Yeah, I'm trying to, like, I'm guessing you saw my terminal?
Yeah.
Yeah, that's not what I'm wanting to.
Oh,
I'll just
okay.
reload. I'll be back in a sec.
Okay.
Cool. Will it work this time? Doesn't seem to.
Would you like me to share for you?
No, it's okay. I'll just copy it into a Firefox window rather than.
Oh, okay.
Then it'll be happy, hopefully. There we go. Cool. I managed to somehow magically share the screen I wanted to share. Where did I? There we go. Sorry about that, everyone. So for the final session today, this is really a chance for you to do a more hands-on, practical, try to play around with Gromacs and see what you can get for it. Like see what sort of see how to run it on Archer 2, how to get it to perform best on Archer 2, some of the things that you can use to make it better. Um, and so this is a series of exercises which will sort of like get you to consider how to get the best bang for your computational buck on Archer 2 when running the Gromacs simulations that we've just been using. So as before, if for whatever reason you want a clean copy of the exercise material, you can find it by running the svn checkout command. And then if you go into the slash exercises slash exercises slash performance directory, you'll find two files, one of which is a Slurm submission script, and the other one is the npt.tpr file, the Gromacs portable binary file that we generated in the last couple of exercises. So below I've put a copy of the Slurm script that you'll be using for this exercise, because this is the point where we're going to be talking a bit about how Archer 2 is set out, how the compute nodes work, and things like that. And the first thing we're going to talk about really is we're going to look at just pure MPI performance. Now, MPI is the is it message passing interface? I can never remember what the I stands for. Holly will correct me in a sec. Um, but it's a way of communicating between between all of the cores on your on a computer, and also allows you to communicate over a network, which means that you can have the cores within one of the nodes in your HPC system communicate, or in your local cluster, whichever. Yay. Communicate with the cores on one of the other nodes within your system. So for this first exercise, we'll just be looking at how much faster can we get our job to run by just increasing the number of cores that we're using. So you'll notice that unlike the previous job we ran, this command here, tasks per node, is set to 1 instead of 128. And that defines the number of MPI cores you're going to be using, or MPI ranks you're going to be using during your simulation. the other thing you might notice is that in the MD run command, I've used the end step flag in order to, and what this flag does is it's a way that you can tell Gromacs during the MD run definition how many time steps you want your simulation to run for. And this can be useful because, as you saw, the building of the TPR file involved you getting your parameters file and sort of like linking it, merging it with your confout.grow, your position file, and your topology file. And if for whatever reason you didn't input the correct number of time steps, it can be a pain to have to redo that step. So instead of that, what you can do is you can define the number of steps you want to run here rather than have to go through all of the steps of rebuilding a system. And you can set that number of steps to be less than, greater than, equal to the initial number of steps. All of them are absolutely fine. Here, in this case, we're going to go much, much less than because we want these simulations to run in a sensible amount of time. So at this point, if you could all run this simulation script to see how long it would take for a job to complete if you're using a single core on Archer 2, that would be really useful. And the aim of this exercise is for all of you to have a look at, well, how much faster does a job run when you use more and more cores? One thing I'd like to do is let me share. That's not going to be a happy action. Give me a sec. If I do that, so let's share this real quick. And let's instead share what I want to share, which is this. Cool. If you ever feel like you need to remember a password, I recommend teaching a course because by the end of it, you definitely remember it. So if I go in here and go into exercises, I will go. So this is the simulation I ran before. One of the things that is always output at the end of every simulation is a certain amount of performance information. And this performance information tells you how much wall time your simulation took to run. So in this case, this simulation took 412 seconds to run. How much core time it took to run. So in this case, this simulation took 105,000 core time. Core time is equal to wall time times the number of cores that were run. And then it gives you performance here. So if you'd run this for an entire day, how many nanoseconds would you have simulated? Well, I would have simulated 209 in this case. What about how many hours does it take to simulate a single nanosecond? Well, hours per nanosecond tells you this. So actually, the answer is one of the questions that we'd previously been asked, which was, well, how long would it take to run my system 100 nanoseconds? That depends on your system. But what we're going to be doing now, if I go into the performance directory, what we're going to be doing now is running the simulation we want to run, but for a much shorter amount of time than we want to. So here we're only going to be running it for, I think it's 20 picoseconds, I guess. Yep, for 20 picoseconds. So really not that long. But from that, we can get an idea of how long it'll take to run or how fast it can get in a day and how long it takes per nanosecond. And we can then use that to get an estimate, a feel, if you will, for how much time we need to give to our job if we want to reach that 100 nanosecond timeline. So with all of that said, with all of that said, if you could all just run this initial simulation and see how long it takes to run, that would be great. And then for the rest of this exercise, for this first exercise, what would really be great is if you could, in the course chat, when that decides to load, in the course chat, I've set up a table. And if you could sort of write down like what you get as your wall time and your performance once all of your simulations are done, performance is nanoseconds per day, then that would be really helpful. And just to remind you, I'll just copy rather than swap. There you go. The output that you get looks like this. Actually, that should be a bit further, shouldn't it? Like that. That should be there. There you go. So, and that should also. Yeah, so you end up with something that looks kind of like that as your output from Gromacs. The numbers we're really interested in are wall time and the performance in nanoseconds per day for all of these various core counts. When you change the core count, that's not the right one. When you change the core count, you'll need to make sure to change, that's the right one. You'll need to make sure to change 2 numbers in your submission script. You'll need to change, first off, you'll need to change the tasks per node to be equal to whatever you want to run. And you'll also need to change where it says -n. Actually, you can just get rid of this. It's probably easier to get rid of this for the simulation. And if you could change then the tasks per node, like start at 1, then maybe try 2, 4, 8, or do them the other way around if you want. Like the idea really is we probably don't have enough time to get all of these if we run them individually, but if we run them together, we should be able to fill out this entire table. And then the other purpose of this exercise is really to give you an opportunity if there were any questions that you might have had that you wish that Holly and I had answered or spent a bit more time on. This session really is the perfect time for you to ask any of the questions that you've not had a chance to ask yet, and we'll happily answer them. Cool, so I'll let you get on with that, and please feel free to edit that page as you get answers, and then we can discuss them once we start getting some answers, like populate the table. So there's a question in the chat which is saying, how can we check wall time? The easiest way to check wall time is if you run tail md.log. The final couple of lines should look like this. And once your simulation is run, the final couple of lines should look like this. And wall time is the bit that's under wall time in seconds. And likewise, performance is the bit that's under performance in nanoseconds per day is the one we're looking for. And the wall time that I've got here is for, let me think, I think that one is for 128 cores. So I can actually just put that in. Ooh, they're looking at other people's wall times. That doesn't, no, that can't be for 128. That's way too slow. Cool. So first of all, let me quickly copy this across, and then I will answer that question. Okay. Great. So one of the questions is, could I please repeat how you need to edit your shell submission file to alternate the number of cores that are being used? Well, actually, I'll quickly show the method I've been using. Also, by the way, thank you everyone who's already filled in the table. We'll be discussing it in a sec, just to go over like what happens when you increase the number of cores. Let's give it its momentary unhappy minutes to, there we go, share screen. So let me see. Yeah, so I did this in a very quick and dirty method, which is some of you will have noticed that I mentioned already that an Archer 2 core node has 128 cores. But for the really small jobs, we're asking it to only use one core for a fair amount of time. It's a really inefficient use of the machine. So what I did instead of just running the script that you used is I set up the following Slurm script. And what it does is, first of all, it runs the 128 core job by itself, and then it launches the 64, 32, 16, 8, 4, 2, and 1, which sums up to 127 cores. It runs all of those at the same time, just in order to make things a bit faster. So there's an ampersand here, which means that they're all running in the background. I've had to, like, the script is a bit more complicated. So for instance, I need to tell Slurm that I want exactly 64 cores, that I want the jobs to be oversubscribed, and I need to define the memory per job. Otherwise, Slurm is going to be unhappy, but that's just Slurm stuff. You don't need to worry too much about that. And that'll just run all of the jobs in one go in one directory, and then you'll end up with a super messy directory like I have here. But all of your log files will be called, 001 proc. That should probably be core rather than proc, to be honest, but there you go. For the 1 core job, and then like 16 is going to be the 16 core job, and they're all running simultaneously, which means that you're going to end up being much more efficient with your resources. I've put all of this in the shared directory. So if you wanted to just copy this script and use this instead of always altering things, you can find it here, and it is called, I think I called it sub MPI fast, because it's just a faster way of doing the MPI thing rather than having to launch a job, wait for it to finish, edit your file, launch another job, or launching multiple simultaneous jobs, whichever. Like, this is just a bit faster. Now, in terms of if you want to actually edit your the script that you got with the files when using the SVN checkout, you would need to edit the tasks per node, and you would need to edit the -n at the start of the right after the srun command. Cool. So let's have another look at that table real quick, because it looked like all of you were really doing a great job at populating it, which is great. And look at that, like, we've already got a ton of information. I'm fascinated by the fact that there's a bit of a discrepancy here, which I suspect might be to do with maybe someone used hours per nanosecond rather. Let's see what I got for that, just to, well, if mine is done. Doesn't seem like it is. Oh, that's fine. Nope, so my 1 core job isn't done. My 2 core job is, so I'll add that real quick. So 2 cores, what did I get? I got 243, which is very much in line with what's already been put there. That looks like I put those there. Weird. I don't remember doing that. Someone must have a similar color to me, and there we go. So for for these results, let's start at the one core results. Looking at these, the wall time seems to be the same in both simulations. However, the performance per day is incredibly different. Actually, I suspect that this one is the correct performance per day. I'll explain why in a sec. And I suspect that that one is probably going to be the hours per nanosecond rather than the performance per day. So I think rather than doing the nanosecond per day, someone copied hours per nanosecond by accident, which is fine. It can be hard to read a bit. And the reason I say that is because, yeah, cool. It looks like I'm not wrong. That's cool. But the reason I say that is because you would expect on low core counts, if your system, unless your system is ridiculously small, you will always expect your performance to roughly halve as you increase the core count from 1 to 2. It should be really close to half. And we're getting a performance of about 7 to 7.3 nanoseconds per day on 2 cores. So I'd expect somewhere around 3.5, 3.8. So that's where that comes from. So in an ideal situation, if you're like, what's the purpose of this exercise? The purpose of this exercise isn't so much to see how much faster you can get your simulation to run as you increase the number of cores. It's to start to get you thinking about whether it's always worth just adding more and more and more cores to make your simulation faster. Oh, excellent, that's been updated. Thank you very much. And so if we look at like, this is quite a small system actually by molecular dynamics standards. This is not the largest system ever. So that means that there should be a point, especially on a machine as large as Archer 2, where all of a sudden we'll start getting, we'll be using way too many computational resources to simulate our to run our simulation. And how do you tell this? Well, the way that you tell this is by looking at the performance. Performance data gives you a lot of information. If you've got a system of fixed size and you double the number of computational cores, you want the runtime to be halved. So you want your simulation to run about twice as fast. And if that's the case, then you're still running at a sensible number of cores. Or if you're close enough to a factor of 2 increase, then you're still running at a sensible number of cores. But as you'll notice here, as we go from 1 to 2 cores, it nearly doubles. From 2 to 4 cores, it's there. We've got one entry, which is 13.8. That's nearly 14. That's nearly twice 7. It still nearly doubles. 13 goes to somewhere around 25. So 25 is not quite twice 13, right? So already it's sort of like dying down, but it's close enough. And then as we increase further, we notice that it goes from 25 to 39. Well, I mean, 39 is nowhere near twice 25. It's nowhere near the 50 that we're expecting here. And likewise, at 32 cores, we get an answer of 65 nanoseconds per day, which is still also not twice 39. So as we keep doubling and doubling and doubling, the speed up that we're getting is decreasing and decreasing and decreasing. And there's a couple of reasons for that, which I won't get into too much detail about. But roughly speaking, with every simulation, with every program, parallel program, there's going to be part of your simulation which can be done in parallel, i.e. can be split over multiple cores. But there's always going to be part of your simulation that has to be done in serial, i.e. can only ever be done on a single core. And as you increase the number of cores that you're using, you are distributing the parallel portion across all of the cores, which means that that part of your simulation time gets faster and faster and faster to the point that it tends towards 0. But the serial time, you're always stuck with that as a constant. And so as you keep putting and putting and putting resources into making your thing faster, you end up getting to the point where the serial part of your code is going to dominate. And once you get that, that's the point where it's really not worth adding more computational resources to your problem, because quite simply, you're not going to get any speed up from it. Your system will be just as will go equally as fast. Now, with something like molecular dynamics, there's actually a second factor to take into account, which is when you're split, which is to do with what happens when you run your system on multiple cores. And what's happening is, actually, I'll go back to this picture real quick, because this will be quite handy. Where is it? It's there. So with molecular dynamics, what you end up doing when you run on more processors, when you run on more cores, is you take your system and you split it up into an equal number of equal parts, such that each processor is simulating one of those parts. But of course, as soon as you do that, then you get the problem that if, say, this processor is running in the bottom right corner, and one of the atoms on this processor moves to the processor in the bottom middle, then you need to communicate that information. The bottom right processor must communicate to the bottom middle processor, hey, look, I'm sending you an atom. And the bottom middle processor needs to say, oh yeah, I got it. And all of that takes communication time. And so molecular dynamics is actually a fascinating problem where it's possible, if you use too many cores, that the amount of time you need to spend having the cores communicating, having the cores talking to one another, becomes greater and greater and greater, to the point that your runtime, as you increase cores, starts to get lower, which means that you can double the number of cores you have and get a longer simulation runtime, so a slower simulation, than if you just run at half the cores. And so this is what this exercise really is meant to emphasize. It's to make you think, well, don't just double everything. Don't just run at the biggest number of cores you can run, or just because you've been told that's the best or anything like that. Maybe before you do this, run a smaller simulation to get an idea of how much faster it goes as you increase the number of cores. Cool. So that was the first exercise. The second exercise is a very similar exercise, insofar as we're going to be looking, instead of just looking at MPI, Gromacs on Archer 2, and actually in general, you can compile Gromacs to do this. It lets you run hybrid MPI and OpenMP jobs. Now, MPI and OpenMP are just two different methods of programming parallel codes. MPI lets you parallelize codes so across distributed memory machines. What that means is it lets you have cores on a node communicate with different cores on another node, whereas OpenMP only lets you communicate on a shared system, shared memory system. So you can only ever have cores on the same node talk to one another. It couldn't talk to any other node. Now, each of them has its advantages and disadvantages. One of the huge advantages of OpenMP is that because you're using a shared memory space, you can communicate a lot faster with the other cores within your area. And Gromacs tries to make the most of this by enabling hybrid OpenMP and MPI jobs, where each MPI rank is able to communicate with another. Each MPI rank has a number of OpenMP threads within it that it can use. And so for this, we'll be using this submission script, which I will simply copy over into my shell. Let me share my shell. By the way, please let me know if I'm going too quickly or for this section. What have I got that I shouldn't have? I'm just going to share my entire screen because this is getting a bit ridiculous. Let me close this. Close this. Everything else should be fine. Sorry for the tunnel. So yeah. I'm just moving everything into a directory to make it a bit neater. And I am copying the text that I mentioned before. Cool, and then I'm going to copy across the npt.tpr file. There we go. So that's not updated, is it? Tasks per node, that's going to start at 128. Let's start at 1. I'll copy that across as well. Cool. I'm afraid I'll have to show you the tunnel again very briefly. But if you want to copy the script that I'm about to use, you can get it from there. Let's go there. Cool. So what we're going to do now is we're going to make use of this hybrid MPI plus OpenMP to see whether we can get our simulations to run faster by doing this. Now, the way you can do this is the n tasks and per node and CPUs per task define the MPI and OpenMP numbers. So if you reduce the n tasks per node to, say, 64, and then increase the CPUs per task to 2, then you will be running 64 MPI ranks, each of which will have 2 OpenMP threads. Now, the number of CPUs per task multiplied by the number of tasks per node must never be higher than 128. And so for that reason, I gave a couple of suggestions that you could try, which I've also put there. So I would recommend, we've already done 128 MPI ranks with 1 OMP thread. That's just exactly the same as here. My simulation runs a little slower than everyone. I wonder why. But what happens if we do a 64.2? What about a 42.3, 32.4? All of these, and I'd be really interested if you could just like pick one of these at random and just simulate that one. And so this number here would go in the n tasks per node. MPI ranks goes in n tasks per node. And then this number here would go in the CPUs per task number. So, I mean, just go ahead and choose one, and hopefully if we all run jobs at roughly the same time, we'll be able to, I will admit to having been overruled on this one, we'll be able to get an idea of how fast these, whether we can get a faster simulation by using hybrid MPI plus OpenMP. Now, this is very system dependent, by the way. There are some systems where you definitely do get a speed up, and there's others where you really don't. That's the right thing. Did I not dispatch? That's running. Good. And again, please do let me know any questions that you have. I'm more than happy to answer them. So I've chosen the 64.2. and it's finished running. So if I look at md.log, when you look through your md.log file, there'll be a really handy, after all of the text at the start, a really handy point where it tells you, so this tells you all of the parameters that you're running, including any parameter you hadn't set. So that's quite handy if you ever think that something's wrong with your simulation. Here it tells you you've used 64 MPI processes and 2 OpenMP threads per MPI process, which is great because that's what I wanted to do. And then if I go all the way to the bottom, it tells me I got a wall time of 9 seconds. And a runtime of presumably about 190. 182. Cool. I'll do the 25.5 next. Cool. So it's still running. It's backed up a bunch of things. And it's still running. And you'll notice that, so I'm running the 25.5 at the moment. And you will notice that whereas all of the runs we've got at the moment, like this one took 13 seconds, this one took 9, 10 seconds, mine is still running. It's been running for about a minute now. And we'll get into why in a sec. But yeah. I think I ran these earlier. I got some scary numbers for some of them. One thing to make note of, by the way, if I go in, look at the /work/TAO59/shared sub OpenMP is, nope, cool, I've done the right thing, that's great. And I have here as well, cool. Nope, there's nothing to make a note of. I just misremembered. Yeah, it's still running. So I got a question. I'm gonna try to view this question without showing the tunnel. That didn't work. There we go, that hides the tunnel. Should the number srun minus n also be changed to, so if you're using the new file, you'll notice I just got rid of the srun minus n. That shouldn't have been there in the first place, actually. Slurm is smart enough that if you tell it what you want it to do here, you don't need to tell it what to do during the srun command. So you shouldn't even need to mention that, if that makes sense. Cool. Hey, it's done. And look at that. Which is about 10 times anything else. So yeah. And, you know, just to emphasize, because you look at this graph and it looked like maybe I got my wall time and my performance mixed up, but no, it is actually that my wall time is 130 and my performance is 13. If anyone's running 3, I think that one takes forever to run from memory. I'll try it now. We'll also quickly check. Yeah, that's fine. And I'll just give it another couple of minutes before we start talking about these results. But yeah, thank you to whoever added the 32 MPI ranks 40 MP threads results, because that really helps to emphasize quite how much of a sore thumb the 25.5 is. Okay, so 3 is going to run for a bit longer. Okay, cool. So in the interest of time, I'll just very quickly talk through this table. So the first thing I want to mention is, so for this particular example, what have we found? Well, we found that using a single OpenMP thread does faster than anything else we've tried. And okay, we don't have any results for 42 and 3, but I'm in the process of running it. It's been running for about 2 minutes and 20 seconds. It's not going to be done in 10 seconds. So I think we can agree that this one wins. Okay. Great. Well, so why bother even considering OMP threads? This answer is twofold. The first part of this answer is these values are very system dependent. So part of the reason for talking about this is to make you aware that this is something I've run systems where actually 32.4 on Archer 2 was ideal. And unless you do a quick test, you'll never know which one is best. So again, this is really to emphasize, please do consider testing your systems before you just embark on running a huge simulation. The other thing I want to mention is, well, let's take the worst performing versus the best performing. Actually, let's not bother with that. But let's pretend for a second that the 32.4 was the best and that it ran in 9 seconds, whereas the 128.1 ran in 10 seconds. Let's pretend these were swapped. If you just go straight in and run on 1281, when it's not the fastest, well, you're getting a significant slowdown effectively, because when you're because in that case you could be running about 30 nanoseconds per day more, which on 30 on 150, that's a significant proportion. It's going to be what? It's going to be about 18% probably. You could be running 18% more than you currently are. That's a lot. So you could be spent and running 18% more of your simulation. Another way to look at it is you could be finishing your simulation 18% faster, using 18% less computational resources to get it. And all it takes to get an idea of this is to do a quick, simple test like we're doing right now. So it's always worth just taking some time to check what the best ideal conditions are for your system. Now, the final reason why you might care about this is because by default, if you don't specify anything to Gromacs, Gromacs will push you to run your system at somewhere between 2 to 6, I think, OpenMP threads. That's the number it pushes for, regardless of what's better. And in fact, you've noticed, hopefully, yeah, this is still running 5 minutes in, that's good. You've noticed, hopefully, that for all of our simulations, we've been using this -NT OMP thread, OMP flag to the Gromacs commands. The reason for this is because if you don't have that flag and you run on a single, and you run with a single OpenMP thread count, Gromacs will crash your job and tell you you're doing something wrong because it thinks that it knows better. Again, I've got issues with Gromacs thinking it knows better than, but yeah. So it's always worth checking these things. I heard a comment. Let me see if I can. So which combinations do you choose if you had to? That's an excellent question. It actually just really emphasizes the point that I'm trying to make, which is it depends on the system. What I would do is I would run a similar set of tests that we've just run in order to find the best and most ideal conditions in which to run my simulation. And I would run a quick test that only takes a couple of minutes, even in the case where you're running the silly system, which is still running after 6 minutes. But I would run a series of quick tests in order to get a better understanding and idea of how my simulation works. And based on that, I would make my decision. You have to run these tests if you want to get ideal performance. And this isn't just true for Gromacs, this is true of any other program. But do quick tests to find ideal optimized conditions and then run your system for long. Cool. So next question that we should maybe answer is, or that we should look at is, well, okay, the time for one OpenMP thread takes 9 seconds, 2 is a bit slower but still within range, 3 is still running and going to be nowhere near, 4 takes a while, 5 takes forever. I heard that there was, give me a sec, there we go. Based on these tests, which one would I say are best? Well, let's spin the question. Which one would you say is best? If I told you try to run the simulation so it runs fastest, what conditions would you use? These are the results. I'm sharing them with everyone, hopefully. You're always trying to increase your performance because faster performance means faster simulations and it means less cost at the end of the day, less computational cost. I'm happy to get an answer from anyone, by the way. While you all think, I will describe very quickly why are 3 and 5, why are the 42.3 and 25.5 so terrible? And part of the reason for that is to do with the way Archer is, the way the Archer nodes are configured. Each Archer 2 compute node has 2 processors. Each processor has 64 cores, and each processor also has a non-uniform memory access region, or has 4 of those per processor, which means that if you think of an Archer 2 core, there are, so if you think of an Archer 2 node, at the lowest level you have the core. The core is able to talk the fastest with itself, the next fastest with the 15 other cores within its NUMA region, the next fastest with the 63 other cores in its on its processor, and the next fastest with any of the cores on any of the processors. And so when you are splitting jobs using hybrid OpenMP MPI methods, you need to be careful to make sure that you are spreading your OpenMP threads within a NUMA region. You want to keep them within this non-uniform memory access region so that they get the fastest communication they possibly can. And when we're running at 3 or at 5 threads per MPI rank, you will always end up having some of the threads straddle a NUMA region, and in some cases straddle a core, straddle a processor. And that will increase your simulation runtime significantly. And we've seen how significantly. It increases by an order of 10. It's quite enormous, really. So I've got an answer to my question. Thank you very much. I totally agree. The best performance that we're getting at 188 to 190 nanoseconds per day happens at 128 MPI ranks and 1 OMP thread. If I were to run this simulation for a longer time, I would use this. Everything else is worse than this. So why would you use anything else? You're always wanting to increase this number as much as possible. Okay. The final 2 exercises I'll leave for you to do when you want, like in your own time. You will still have access to Archer 2 after this course. So if you're interested in these, you're more than welcome to. But I'll briefly talk about them. The first one is we've been running all of our simulations with this hint, that should be no multi-thread. We've been running with this hint, no multi-thread the entire time. So multi-threading is a special thing that's, that you can do to essentially allow each core in your system to act as if it's 2 mini cores. And sometimes it works really well, and sometimes it doesn't. So this exercise is really to get you to test whether pushing the Archer 2 system to its fullest will give you the best, fastest simulation time. And then the final one is to do with load balancing. You know how I described earlier how the system is split between processors? There's a couple of ways of doing that. The easiest way to think about it visually is, well, if you've got 4 processors, just do an X down the middle, and each processor gets, like, you'll have the top right, bottom left, top left. But what happens if your system isn't uniformly dense? What if, the bottom right processor has twice as many particles as the top left processor? Well, the way Gromacs gets around this is that by default, it uses a setting called dynamic load balancing. And what that does is it sort of like messes around a bit with the boundaries to make sure that all of the processors have roughly the same number of particles within it. And that also ensures that all of the processors are doing roughly the same amount of work. And the aim of this exercise is to show how much of a difference dynamic load balancing makes. So if you get rid of it, which you can do by just setting the -DLB no flag when, oh, it's done. Here, so MD run, you could add just minus dynamic, maybe if I press insert first, that would work. Minus DLB no. That stops the dynamic load balancing. And so you'd expect your simulation to go slower. And the aim of this exercise is to show you whether it goes slower and how much it goes slower. So with that, the takeaway message from just these general exercises is using hybrid MPI with OpenMP does affect performance. And when you're running hybrid jobs, the placement across the NUMA regions is really important. But actually, the real key takeaway point is please do some quick performance testing. I know it sounds weird to say use some computational resources to see what the optimal situation is, but it's a small investment that will get you to save so much down the line that it's always worth doing. And this isn't just true for Gromacs, this is true across the board. Okay, so with that, we reach the end of our lesson, of our session. And I just wanted to mention real quick what the next steps that you can do are. I've noticed a typo there, but that's okay. So Okay, we've spent a fair amount of time talking about Gromacs, how to run MD simulations in Gromacs, how to prepare your simulations in Gromacs, how to analyze the data from your Gromacs simulations. Well, where next? What if you want to do more, learn more about using Gromacs, or what if you actually just want to go out there and use Gromacs for your own simulations? Well, there's an awful lot of stuff that we've definitely not covered, which can be found in the Gromacs manual. Gromacs manual, yep, you can just click on documentations, and there's just a ton of stuff there. You've got the Gromacs how-to guides, you've got release notes, installation guides, user guide, and if you click on the user guide, it sort of gives you loads of information. You can also, any command that you're interested in learning more about from Gromacs, you can just type gmx, let's do md run, for instance. And you've got a page and it tells you every single flag that you can use. There's a description of everything. And then it sort of tells you in a lot more details what they are at the bottom. So the Gromacs manual is a great starting place. The how-to section, yep, the how-to section is also super useful when it loads. Let me just, I heard there was a question. I'm just wondering what's the biggest advantage of Gromacs over LAMPS? I'll answer that after this section, if that's okay. But yeah, so there's a how-to section. There's the Gromacs best practice guide, which has two parts which are quite interesting. The first one is the suggested workflow, which Holly and I definitely used as inspiration for a lot of this course, which again just talks you through how to go from preparing your system. It even mentions things that we didn't cover, like what if you want to use your own force field as opposed to one of the ones that Gromacs wants you to use, preparing and solvating your system, adding ions, running your simulation, etc. There's a lot of stuff we've covered. There's some extra bits we've not covered. The other great thing that this guide has is it has the performance cookbook, which is giving information about the performance of a set of Gromacs benchmarks on various systems. And with those, you can sort of see like how fast they ran, whether they worked better on CPUs only. I think they've looked at a number of HPC systems, some of which have both CPUs and GPUs. I think for any questions about this, I think, Stephen, you were quite involved in this, weren't you? The next one that I really want to point towards, and that we also used as inspiration for a number of things, and it's an excellent set of tutorials, is the Justin Lemkool tutorials, which so they do go from the most basic how to run your first Gromacs simulations, kind of like we did now, to other things like how do you run umbrella sampling, what about protein ligand complexes, what about biphasic systems, and you can kind of like click on them and do the tutorials, and again, it sort of explains step by step what you need to do. It explains why you're making the choices you've been making, and it sort of just talks you through all of the simulation steps. And it comes with a fantastic living journal article, which just explains in more depths and more details exactly what each of the practicals is trying to get you to understand and do. And then finally, if you still have questions about how to use Gromacs, there is the Gromacs forum, where you find loads of information about any announcements that Gromacs might have, any user discussions, any questions that some people have had. And the great thing about this is that it's used by both the Gromacs community and it is checked out by the Gromacs developers. So very often you'll get answers to your questions very quickly. The other thing as well is it's quite, it's got a search function. So I don't know if I go for MD run, it sort of like gives you all of the questions that were ever asked about MD run, and then you can check whether someone else has asked your question before you, and hopefully get the answer without even having to ask it. Now, finally, for this course, we've been using an awful lot of Archer 2 time. You were all invited to apply to access to a TA059 account, and there's a small amount of budget on there. you will still retain access to this account for a couple of months, so that if there was any part of this session that you wanted to try out again, or if you wanted to run, even do some testing for your own systems, that sort of thing, you're welcome to use that. If you have any questions about using Archer 2, the first place to check is the Archer 2 manual. We've been on it before, but it's a really good user manual that tells you a bunch of information about Archer 2. Chances are, I'd say probably 75% of questions are probably answered here. If it's not answered here, or if you can't find it, then you can always contact the Archer 2 support team at support@archer2.ac.uk, and we'll be happy to help with any of your Archer 2 questions on there. And then finally, I just want to quickly mention that as part of the Archer 2 program, there is the Archer 2 training, which you're all aware of because you're currently attending one of the Archer 2 training sessions, where there are a ton of useful information. You can register for upcoming courses. For instance, I think there's an introduction to modern Fortran, which is happening next week, I guess. That must be next week. Yes, next week. HPC for CFD when you're using code Saturn, also happening next week. There's a number of interesting talks, and the best thing about this is that if you go, not in course description, but in course repository, every single course that's been run on Archer 2, including, for instance, the advanced use of LAMPS course that I ran last week, was last month actually, is available. And for every single course, we have the course material still available, and we've got videos of all of the sessions that have been run. So there are a number of interesting courses there that you could explore. Cool. So I guess with that, I will unfortunately have to make you suffer the tunnel again as I stop sharing my screen. And I believe that that is... I believe that we've reached the end of the session here. So there's one question that I didn't answer, which is, I'm just wondering what's the biggest advantage of Gromacs over LAMPS or LAMPS over Gromacs? Both of them seem so powerful. So Gromacs over LAMPS, so both of them have their advantages depending on your system, from my experience. If you for anything biochemical, Gromacs is fantastic. It's got all of the nice, neat improvements to your software, which means that actually you end up getting a wall time per simulation time step, regardless of the length of your time step, which is probably slightly shorter than for LAMPS. So you can run either bigger simulations at the same speed at which you'd run them in LAMPS. You'd run the smaller simulation in LAMPS, or you can run the same size simulations faster in Gromacs than you could in LAMPS. However, this is only for biochemical systems. For anything that's more physical chemistry, or for anything that's more physical chemistry than biochemistry, LAMPS is much more versatile, much more intuitive to use, much more easy to tweak than Gromacs, in my opinion. I've used LAMPS much more than Gromacs, so that probably, makes me somewhat biased as well. Please do bear that in mind. But yeah, I guess with that, I'd like to say, well, first of all, thank you to all of you for coming to this session and asking all of the questions and participating. It was great teaching you about Gromacs. I hope you all found something interesting from this. I'd like to ask again to please make sure to fill out the feedback so that we know how we can improve this course for next time. I'd like to definitely thank Stephen, Holly, Andy, and Alexei, who all helped with the running of this course. And please, by all means, do ask us any questions that we've not covered over this course. We're more than happy to answer them. And I'm not sure, Holly, whether you had anything else you wanted to add.
Not really, no, just thanks everyone for coming. If you have any more questions, we'll stick around for 5 or 10 minutes, and if you want to ask them in the chat. we can answer them. Yeah, and also fill in the feedback and let us know how it was. Sorry about the timings. It was a little bit longer in some places and shorter in others, but this is a new course, so we weren't exactly sure how it would all run. But yeah, thanks.
I noticed that there's a... Sorry, I'll let you answer.
Oh, the last question?
There's two questions. I'm happy to answer either or both, or you can, whichever.
Okay. I'll let you answer. I can't quite see them.
Sure. So the first question is, how can we get an acknowledgement certificate? I believe for acknowledgement certificates, if you could email, I think it will be training@epc.ed.ac.uk. Then just say that you've attended this course and ask about attendance certificates. You should be able to get one that way. The other question is, how does one access Archer2 after this deadline? So that's an excellent question. Let me very quickly share my screen again. If you go on the Archer2 website, I will post a link in the chat. There you go. There we go. And click on support and access, user support and access. It will tell you all of the ways that you can get access. So Archer2 is a machine that's paid for by EPSRC, the UK's Engineering and Physical Sciences Research Council, and anyone can apply for Archer2 time as part of an EPSRC grant. There's also a number of other ways to get Archer2 time. So for instance, there is the pump priming call, which is always open, where you need to fill out an application to explain what sort of jobs you'll want to run. And once that's done, you will get up to 4,000 node hours for up to 6 months. There are calls, for instance, the pioneering call, which are open and have a deadline. And whenever those happen, you can apply for Archer2 time as part of these calls. Likewise, for the access to HPC call, there are also ECSE projects where if you have a specific code that you're wanting to port to a HPC setting, so let's say it works on your local cluster, but you'd like it to work on a HPC high performance computing system, then you can apply for an ECSE grant to get not only some time on the machine, but you'd also get some time from research software engineers to try to help improve your code and make sure that it works efficiently on there. I think that answers your question. Please do let me know if not. As an independent PhD student, I think the easiest way would be to discuss this with your PI. First, discuss it with your PI and have your PI or you both contact us at support@archer2.ac.uk, and we will see if we can work something out. We probably could.